The abundance of the chemical elements is a measure of the occurrence of the chemical elements relative to all other elements in a given environment. Abundance is measured in one of three ways: by the mass fraction, the same as weight fraction; by the molar fraction, fraction of atoms by numerical count, or sometimes fraction of molecules in gases; or by the volume fraction. Volume fraction is a common abundance measure in mixed gases such as planetary atmospheres, and is similar in value to molecular molar fraction for gas mixtures at relatively low densities and pressures, and ideal gas mixtures. Most abundance values in this article are given as mass fractions. For example, the abundance of oxygen in pure water can be measured in two ways. The mass fraction is about 89%, because that is the fraction of water's mass which is oxygen. However, the molar fraction is 3,333%, because only one atom of 3 in water, H2O, is oxygen. As another example, looking at the mass fraction abundance of hydrogen and helium in both the universe as a whole and in the atmospheres of gas giant planets such as Jupiter, it is 74% for hydrogen and 23 to 25% for helium, while the atomic molar fraction for hydrogen is 92%, and for helium is 8%. In these environments, changing the given environment to Jupiter's outer atmosphere, where hydrogen is diatomic while helium is not, changes the molecular molar fraction of total gas molecules, as well as the fraction of atmosphere by volume of hydrogen to about 86%, and of helium to 13%. The abundance of chemical elements in the universe is dominated by the large amounts of hydrogen and helium which were produced in the Big Bang. Remaining elements, making up only about 2% of the universe, were largely produced by supernovae and certain red giant stars. Lithium, beryllium and boron are rare because although they are produced by nuclear fusion, they are then destroyed by other reactions in the stars. The elements from carbon to iron are relatively more common in the universe because of the ease of making them in supernova nucleosynthesis. Elements of higher atomic number than iron, element 26, become progressively more rare in the universe because they increasingly absorb stellar energy in being produced. Elements with even atomic numbers are generally more common than their neighbors in the periodic table, also due to favorable energetics of formation. The abundance of elements in the Sun and outer planets is similar to that in the universe. Due to solar heating, the elements of Earth and the inner rocky planets of the solar system have undergone an additional depletion of volatile hydrogen, helium, neon, nitrogen, and carbon, which volatilizes as methane. The crust, mantle, and core of the Earth show evidence of chemical segregation plus some sequestration by density. Lighter silicates of aluminum are found in the crust, with more magnesium silicate in the mantle, while metallic iron and nickel compose the core. The abundance of elements in specialized environments, such as atmospheres, or oceans, or the human body, are primarily a product of chemical interactions with the medium in which they reside. Subscribe our channel for more such informative short video.